Go ahead and start this out. Ready? Okay, cool. Hi, so thank you for coming today. And like Christina said, we're going to be learning about Git today. This talk is going to be pretty demo heavy, and we're going to go back and forth between my terminal and these slides. And you're going to be hearing my keyboard a lot, so cool. And first things first, actually, let me see if I can get a little chat box, a place where I can see it. That's not going to be a good place because you all want to see the screen, right? Okay, yeah, you should be able to respond there. Perfect. And yeah, hopefully we'll be able to participate a little bit through the chat. And the first question that I've got for you all is, can everyone read this? Which shouldn't be an issue since this is all, online. I imagine everybody can read this one. Cool. Perfect. So my name is Camilo. You can find me on Twitter at cam.bio, or you can find my website, cam.bio, which I always like as a little pun because it also spells out cambio. But yeah, let's get into Git. So Git is a version control system, and its job is to keep and track a history of all the changes that you make to files inside of your, usually your code repository. You can track any kind of text file, actually. And I'm sure a lot of you are using Git every day, and you might even be using something else. I used to use something called SourceSafe, which was a big hassle. I know other people use SVN, Subversion, or they use Mercurial. And they're all viable. But today we're going to be sticking with Git because Git has kind of taken over the version control world. But why should we bother learning what's going on in the background at Git of our Git repository? Is it just out of sheer curiosity? For my part, I don't really, that's just not a very big motivating factor for me. I'm not that curious about how my tools work. If it works well, then I'm happy, I just want it to work right every time. But the fact is, Git doesn't work right every time. If you take a second and look at this XKCD comic from 2015, it basically nails how mostly you're going to learn Git when you're first starting out programming. You're going to learn a few magic commands like git add, git commit, git push. And then when something goes wrong, someone tells you, what you do is you take the whole folder, save it somewhere else, save a copy, and delete your directory and re-download the whole repository. It's not really a very satisfying answer to your Git problems, though. And the point of this talk is that if you have a good mental model for how Git works, then that's going to help you, make good, meaningful searches so that then you can figure out your problem on your own or ask good questions to your, boss or mentor or coworkers or whatever. And we need good mental models for every other tool, kind of like Christina was saying. You want a good mental model for how your programming language works or your database. So in JavaScript, for example, you want to have a pretty good mental model of the event loop. You want to have a good mental model of how callbacks work, as well as, infamously, how context works in JavaScript. So then you can always keep track of what this is referring to. Now, Git was originally a toolkit for a versioning system instead of the versioning system itself. Now it's, now it's both really. But because of that, there are two kinds of commands in Git. There are the porcelain commands, which are ones that you already use day to day. And those are meant for human use. Do you know any porcelain commands offhand? I already mentioned two of them actually a little bit earlier. But yeah, if you want to throw any other commands that you already use in Git, they're most likely into the chat, they're most likely porcelain commands. So things like git add and git commit, which I already mentioned earlier, those are porcelain commands. And then there are plumbing commands. And plumbing commands are low-level commands that are not really meant for human consumption. They're meant for programming with. So you would pipe them together in scripts and use them that way. So of course, that's primarily what we're going to be using today. So it's demo time. And like any good magician, I'll go ahead and show you that this folder is completely empty. And let's start with, the way you start any Git repository, which is git init. And we can even get the message that tells us exactly where all our Git stuff is going to be, which is going to be this .git folder. Let's take a look inside of there. So we've already created a couple things for our Git repository. There are some things you probably already use one way or another, like the config file is where you can set, your name, your email address, and things like that. Or you could add remote repositories, set up branches. There's a lot of things that you can do inside your config file, but that's not what this talk is about. Another thing that you might have already used is the hooks directory, which let's take a look at what's inside the hooks directory. There are a bunch of sample files, but the idea here is that the things inside your hooks directory are scripts that will run certain events while you're using your Git repository. So the most famous would probably be a pre-commit hook. And that's a good place where you could add, code checkers, run tests, run linters, but rather famously try not to impose that on your coworkers because eventually they're going to hate you for slowing them down. Now, for this talk, though, we are going to be looking primarily at the refs directory, the objects directory, the head file, and the index file, which doesn't exist yet, but we're going to create it later. And let's start off with the building blocks of Git. So all of these slides have Pokemon on them. So who's that Pokemon? It's Ditto. Now, things start out in Git with blobs. So let's go back to the demo. We'll start out by creating a new file called pokemon.txt. And what we're going to put in that file is just the word Ditto, right? So it's already the star of the show. And to take a look inside, that's all that's there. Now, what we're going to do is take a look at our very first plumbing command, which is the command hash object. Now, what that means is pretty straightforward. It's going to create a hash and it's going to create an object in our Git repository. And we're going to give it the pokemon.txt file, which again only has Ditto in it. What we get back is a hash, B97. Now, this value that we get back is going to be the key, because at the end of the day, what Git is in the backend is a key value store or a content addressable file system. So the contents of your file with some headers are hashed and then put into your .git directory in the objects directory. And then this hash is used to name that file, and that's going to be how it refers to it. Now, Git uses the SHA-1 hashing algorithm. And to kind of take a step back and explain hashing algorithms, a hashing algorithm is a math function that's going to take any data of any size and give back a result of the same size. So SHA-1 is a pretty well-known one, and you've probably already used hashing in your web applications to store passwords. Usually what you want to do is store a hashed version of your user's passwords in your database. And in that way, when and if, let's say if your database gets stolen, you haven't leaked out all your users' passwords because you never stored the actual password, you stored the hashed password. And let's prove that this is the SHA-1 hashing algorithm. Now, what we're going to do here is we're going to take the text blob 6/0 and Ditto and throw it through the SHA-1 hashing algorithm. Now, why is it this instead of just the word Ditto? Well, that's because this is what Git actually stores. It stores the kind of object that it is, which is a blob. It stores the length of the content, an escape key, an escape character, and the actual content itself, so Ditto. And if you're a quick counter, you'll see that Ditto is actually 5 characters. So why is this 6? It's because of this escape character, which separates the headers and the metadata from your content. But if you run it through, you see we get the same exact hash, and that's what Git uses. So what does Git do with this? If you're not familiar with find, what we're going to do here is get a list of all the files that are in the Git objects directory. And let's take a look in there. Well, in our Git directory, there's the objects directory. And in there, it's created something that looks very similar to our hash, which is it took the first 2 characters and created a directory out of that. And then it used the rest for the file name. So why does Git do that? It's because some operating systems and file systems will have a limit on the number of files in a directory, especially older file systems that are used to having smaller room for integers. In that way, Git's workaround is quite simple. Go ahead and use the first two characters, and that gives you enough files that it's really, not going to be a problem. Now, what happens if we view the contents of this file? Let's run Git on this file that we just created in the objects directory. It's gibberish. What we actually have stored there is a compressed binary version of the same file that we had before. And now we're going to have to use another plumbing command in order to see what they look like. So that plumbing command is going to be cat file. So let's use the hash. Everything you'll see is hashes in Git. The content, exactly the content that we had before. So we can refer to a hash and get exactly the object that's in the objects directory. And in that way, everything is saved. It just brings these things right out. I actually don't recommend anything. I have the IDE use do all the linting and stuff. So in my case, I use Vim, and yeah, I use like a thing that'll just keep linting it as it goes. Though I think it lints it on write. And that's worked out pretty well for me. Thanks for the question, Christina. And yeah, if you have any questions, just go ahead and throw them in the thing. I have questions for you also. I'll probably address them right as we go. So let's go ahead and add a little bit to our Pokemon.txt file. What we're going to do is add the word pseudowudo to our Pokemon.txt file, and I promise you this will pay off in a little bit. Now, if we look at Pokemon.txt, you see it has two Pokemon in it, Ditto and pseudowudo. Let's run hash object again on our Pokemon.txt file. What do we get except another hash? It's hashes all the way down, which is a joke I'll probably make more than one time. Let's run cat file on that hash to see what's inside. And it has Ditto and pseudowudo. Now, this was really interesting to me when I was writing this talk, because I had always thought that Git stored the differences between files and kind of built your current content based on that changing history. But actually, it stores snapshots of the file in this objects database, which again, if we take a look at the objects, now both of these here referred by their hashes. And that's how Git stores things. It'll always store all your content as a snapshot. Now this might be a bit of some color change. Go ahead and create this lyrics.txt file. And you're gonna, usually if this were in person, I would have asked you to sing me the song. So those are the first two lines, of course, of the Pokemon theme song. And we have our lyrics.txt file there next to our Pokemon.txt file. Now, if we run our hash object again, and -w in this case is for writing it to our objects directory, we'll pass in our lyrics.txt file. We get, of course, yet another hash. And now we're cooking with gas. We've got two files in our repository. We've got three objects, not just two, but three, because this is the first object that we created, and Git doesn't let go of anything. So we have three objects in our objects directory. And all the same, though, there's actually something really important missing from here. All our content is here in our objects directory. But can anybody tell me in the chat what is missing? Like, what is missing from our Git repository right now? Something that we like to use, to talk about the files that we use, and that's file names. So what do we use for file names? We use trees. So this is a pseudowudo. Here's another Who's That Pokemon. So Git stores file information like the file names using trees, and then it stores the file contents using blobs. And trees can also pull double duty. They don't just store the file names, but they also store tie several files together, and they also store directory information. Of course, you want that information because when you create commits, you want to be able to have multiple files in your commit instead of just one blob. So how do we store a tree? First, what we have to do is create an index, and that is going to require a new command called git update index. We're going to add our lyrics.txt file. Now, the index file is, so I promised you that it was going to exist, and let's take a look in our Git folder. Yeah, we have the new file called index. And this index file is going to be what we commit later on. So let me show you something a little cool here. Oh my gosh, what are you doing, buddy? Okay, that's very strange. I like, what is going on with my mouse? Well, that's a shame, but we'll probably be seeing that window quite a bit then. Let's run. Hold on, let me just disconnect this and reconnect this real quick. Sometimes my equipment gets a little bit finicky at those times. Okay, all good now. Yeah, so let's run git status. We just ran update index, and now we run git status. Can anybody tell me what update index add kind of works the same as? It works pretty much the same as git add would if you were using it, git normally. So we had a file before, like right now, our Pokemon.txt file says ditto sudo wudo, right? So currently we have that, but we also had a file in the past that just said ditto. Now, how can we leverage the fact that we have a Git object in our object directory that just has ditto in it? That's this one right here. Well, we have the hash for it. So let's abuse update index a little bit and add something from the cache. So that's cache info. We want to give it the file permissions, which you might know if you've ever had to do any of your own like hosting or anything like that. And I'm gonna scroll up and find the hash for our, here it is, for our first version of the Pokemon.txt file. And we also add in the name of our file, Pokemon.txt. And we're going to update the index with that. So now if we run git status, you're going to see we have these two files are in our staging area, Pokemon.txt and lyrics.txt. But rather interestingly, it also notices that Pokemon.txt as it exists right now in our file system is not the same as a Pokemon.txt that it has in the staging area. And that's because when we added it using the hash that's in our objects directory. And that took it from well, it took that version that just says ditto. Now let's keep on moving and create our tree object from the index that we've created here. And we're going to use a new plumbing command called git write tree, and that's all that it needs. And of course, what do we get except for another hash? Now, let's use cat file and take a look at what is in -p, at what is in this hash. We have a list. We have a list of blobs. So each, there's two things here, just like we saw in the staging area. There's lyrics.txt and pokemon.txt. In our tree, there's lyrics.txt and there's pokemon.txt. And there are the hashes that correspond to each. There's the kind of thing it is, which is a blob object. And we have the file permissions for each. So you can see how Git can pretty easily take a look at trees and rebuild your directory when it's, you're pulling down changes or anything like that. This is what's happening. This is what Git is reading. Now, another thing that trees do is act as kind of an equivalent for directories. So if we make a directory, we're going to make a directory for dragons because dragons are very cool and they deserve their own directory. And we'll create a new Pokemon.txt file inside of our dragons directory. Now, if we run update index and add our new Pokemon.txt file inside of dragons, of course, we're going to write tree again to create a new tree object. What do we have? We have the same content that we had before, which is to say these two blobs with Pokemon.txt and lyrics.txt. But we also have another new object, which is a tree object. And this tree object is going to be given the name dragons, and we have a hash for that. So let's take a look at what's inside of that hash. It's another tree, so this is another list. But in this case, it has a Pokemon.txt file, and it has something that we haven't really seen before, which is a hash that was actually created. Didn't we skip a couple steps? Yes. This was update index went ahead and hashed our Pokemon.txt file inside of dragons and created a new blob object for us. So even as we're using these plumbing commands, we're not doing everything ourselves. And if we take a look at that hash, we can see the contents are just the word Dragonite, which is what we wanted. And in case you're wondering about Git keeping pretty much everything, let's take a look in our objects directory. Yeah, it's starting to blow up quite a bit. A lot of hashes have been made, and these represent various trees, blobs, and well, that's it actually. So we can see from this information here that trees can act as directories, and they also act to tie files together as blobs. So what's left in the way that we would normally use Git if we were using Git day to day? Well, the next step is commits, right? And I know for myself, this is when I start thinking, this is what I thought was the atomic unit of Git, like all I care about myself are the commits. And if you want to play Who's That Pokemon, this is a clef key, which I thought was a good metaphor for a commit. It's, you're locking it. Anyways, so now that we have things in our staging area, we can build our commits and create a commit history. So let's go ahead and create a commit. I'm going to grab something from history. So what we have here is our commit message, first commit. What we're going to do is use a new plumbing command called commit tree. And this is the hash of the tree that we just created with Dragonite, remember? This is the tree that in question. So let's create a commit out of that. And of course, what do we get back but another SHA-1 hash? This SHA-1 hash, let's take a look at it. 22F is going to be in our objects directory alongside everything else. And let's go ahead and use this along with git cat file -p and take a look at what Git saves in its commit. It saves kind of all the information that you're used to seeing: authors, committers, the time. Oh my gosh, let's just clear that out of the way. There we go. Author, committer information, the time of the commit, your commit message, and the tree that your commit is referring to, which is kind of the most important part here. One thing that's interesting is you probably saw me a couple times. I use the reverse search to go through my history to grab stuff. And that's because if you have the same exact content with the SHA-1 hashing algorithm, you get the same exact result. But I can't do that anymore. And the reason why is this little number, these numbers right here. I can't stop time for this talk. Therefore, these commits are happening at different times, which means the content is different, which means that the SHA-1 hashes that I get back are different. So you can see why it's a good way to to store things. Now, let's make a tree with the latest. Let's update our index so that we have the latest Pokemon file. Right now, it still just has the version with only Ditto in it. So sudo wuro, let's get into the action and add our latest Pokemon.txt. Take a look at Git status. Now it knows that Pokemon.txt is up to date with the Pokemon.txt that's in our file system. We'll run write tree, and of course get back another hash. And let's go ahead and create a second commit. Again, I can still use the history search here because the Pokemon.txt file is the same as before, and I'm creating the tree, not the commit. But again, we're using the plumbing command. We've changed our git commit message to second commit, and we're using this new tree that we just created. We get back a new hash. And so you're going to see me scroll quite a bit, even more than before, in order to get some of the old hashes that I had before. But let's take a look at what happens with git log. One of the things that you can do with git log is send it to F. You can send git log a commit hash, and it'll do the git log history from that commit. So let's take advantage of that to see the git commit history based on our first commit that we created, which is the 22F1, and the second commit is 1cc. Let's, you know what, I'm going to write that into the chat. And that'll help me find it later. So if we run git log with this, great. We see the git log as we expect it to be. We see, nicely formatted now, the author information, the time that the commit was created, our commit message, the changes that were made, and the commit hash. So that's great. And let's do the same thing with our second commit. And if you've never used -- stat before, that doesn't really do anything in particular except show you this information here. So git log has a ton of options for various things that you can change in the output. Here we see, again, the commit information that we expect. It's got the commit hash for the second commit. However, there's something missing here, right? This is the second commit that we created, and it's missing our log history, our commit history. We created a first commit, we created a second commit. Why isn't it tying those two together? And that's because this commit is actually missing the information of what came before it. You take a look at the files changed, it still thinks 3 new files were created. So let's take a look at what we might do for that. That's what I'm going to type out. Type in the commit tree. And we'll have basically the same, actually, let's not type it out. This same commit, the same commands that we had before. However, we're going to add a little extra, which is the -p flag. P for parent in this case, and we're going to send it the commit hash that we have for our first commit. And that gives us a whole new hash, of course. Now, if we take a look inside it, let's move some of this stuff off the screen. Inside of our new commit, we have the same information as before, the same commit message, the same author. Well, the time has changed because we created a new commit, and the same tree hash. However, now it has this parent line, and it has a reference to the previous commit. So if we ran log stat against this commit, well, we have the kind of log that we expect to see, which is, the author, the date. But we have both commits here. So the first commit, it says it added those 3 files. The second commit, it just changed 1 file. So that's kind of the git log that we expect to see. So to recap, we have blobs that contain the contents of the file, and those blobs are snapshotted and saved in our objects directory. I'm sure if I find it, this is the very first blob that we created, the B9, 7, and so on. Then blobs can be put together into trees in just a regular, top to bottom list. Trees can be combined with other trees to create our directory structure. And that's going to be, well, a tree data structure is how that looks. And then commits are built from trees, and they can reference each other in more of like a linked list, a singly linked list type data structure. Now then, let's run git log without any commit. Nah, there's nothing here. Your current branch main does not have any commits yet, which is a little offensive, I mean, I spent all this time creating 3 commits. So why isn't it being recognized? Here's another who's that Pokemon? It's Rotom acting like a Pokedex. In this case, to talk about references. So references is how basically branches work, and how Git gives us a good way of taking a look, like a way of naming commits, so then we don't have to remember a ton of hashes. So let's start out by looking in our refs directory in the Git directory. And what we have is the refs directory itself is empty except for 2 other directories, one called heads and one called tags. As you can probably imagine, tags, whenever you tag a release in GitHub or anything like that, that's where your tags are stored, are right there in tags, and it works the same as heads. You just use them for different things. It's a convention more than it is a real functional difference. On the other hand, if we take a look inside of, no, that's not what I wanted. With the heads folder, there's nothing in there. So let's go ahead and add something in there. What I need right now is the last commit hash that we created, which is going to be this one, 48A. And let's create a file inside our heads directory called OK. And we're going to put that hash in it. So to kind of prove that that's what's happening, let's go ahead and take a look. Inside, it's just a file with nothing but the commit hash in it. And what that's going to do is that creates a reference that we can use later on. So if we ran git log, and one line is just going to make a smaller version of our git log, we can use poke instead of the commit hash and get the same git log as what we had before, with all the same commits that we had before. So you can see how that's going to be pretty useful for us, mere humans that can't memorize these hashes. Now let's take a look at another file that I told you that we would be taking a look at that probably sounds pretty relevant right now since we're looking at a directory called heads. Let's look at the actual head file. The head file says it's taking a look at a ref, and that ref is in refs heads main. But if we take a look inside of our heads folder, there's actually no main there. And that's what Git was talking about when it says my current branch main doesn't have any commits yet. There's nothing to reference inside of refs heads that is called main. So what happens when I run checkout? Checkout is the command that we use to check out the branch, another branch, or another commit, or another tag, or anything like that. So what has happened to our heads file now? Well, it said it's looking at a refs, and now it's looking at refs heads. Okay. So now we can see exactly how branches work, which is basically a file in the refs heads directory that refers to a certain commit. And now if we tried to do git log, it works exactly the way that we would expect, because we are actually on a certain branch. Let's do it. Now then, if we go ahead and do something like git checkout this commit hash, wow, Git was not happy about that. He told us we are in a detached head state. So what has happened here? Let's take a look again at our head file. Well, instead of having a reference that it's using. Now it's using commit hash directly, and it's detached from any kind of reference or tag that you might want to use as a Git user. Therefore, here we are, detached head state. So it's actually pretty simple. It's a very scary message that makes you think of guillotines, but in reality, it's just that that head file is pointing to a hash that doesn't have a reference. So if you use checkout, you can get back to something, more reasonable. Now, armed with this knowledge, other commands become easier to conceptualize. So cherry pick makes a little bit more sense to me. When I was first thinking about cherry pick, I had, in my head kind of an object-oriented approach where I was thinking like, I guess I didn't understand why when you use cherry pick, it creates a new commit. And for those who don't know, what cherry pick does is you have, a commit on another branch, the commit hash of that commit, and you want it on your branch. So you use cherry pick, you give it the commit hash, and it adds it to the end of your branch that you're working in and creates a new commit. I didn't understand why it was doing that, but now it makes a lot of sense. You take that commit, you get the tree hash from the commit probably, and I haven't actually looked into the source code to make sure this is exactly how it works, but you get the tree hash for that commit, and you give it a new parent. And because of the fact that it's going to have a new parent and it's going to have a new time, it's going to have to be a new commit. Otherwise, the whole SHA-1 hashing thing isn't going to work, right? And rebase probably follows a similar line of thought. New parents mean new commit hashes at the very least. And that's it. That's as far as this talk goes. Some acknowledgements. Pro Git is still, as far as I know, the best book on Git that exists by Scott Chacon, one of the early employees of GitHub, actually. And a lot of this talk is inspired by a similar talk called Dissecting Git's Guts by Emily Gier, which I highly recommend watching because she's a good speaker and goes a little bit further into Git than this talk does. So I'm down for questions, and that's it. That's the whole talk. Okay, that's not showing anymore. I cannot hear you, Christina.
Thanks. Sorry about that. Thank you, Livia. So if any of you have any questions, go ahead and drop them in the chat. I do have a question. So generally, when you do check out a commit, a specific commit, and you're in a detached head, what's like a use case for that? And how do you, if you make changes, how do you get yourself out of that detached head and keep those changes?
The second part is, so getting to a certain commit, kind of makes sense to me in case that happens to me when I just want to look at a commit at a certain point in history, right? Or a file at a certain point in history, I'll go ahead and check out at that specific commit hash. Though these days I'm probably going to use GitHub's view for that instead. But yeah, that would be the main use case for me to check out a specific commit hash. There are also situations where that kind of thing can happen. I think if you have like a conflict while you're rebasing, it'll put you into a detached head state to fix the conflict, and then it gives you instructions. You have to add, fix the conflicts, add your files, and then commit it. So that creates a new commit in order to keep those conflicts from happening. So those are some ways that you could end up in a detached head state. The one while you're rebasing is particularly scary because it's, I don't know, it's hard. I don't know, it just shows up. You expect everything to work and it just shows up. You're like, oh man, I broke something. As for how you get out of it, I mean, it really depends on the context. I could imagine you could make your changes and then use git stash to temporarily take your changes out and check out a branch, and then git stash pop to bring your changes back. And then you resolve any conflicts that result as a part of that. So that would be one thing. If it happens if a detached head state happens as a part of git rebase, then there's a set way. Same with merges. There's a set way to do it. You fix your conflicts and then create a new commit.
I definitely learned a lot. I pretty much didn't know any of those commands except for git log, of course.
Yeah, thanks for the question, Bert. And yeah, same here. Before or seeing that other Emily lady's talk, this was all a mystery, and now it all makes sense. Like everything's back there. I understand why Git is so reliable, because everything is just saved back there, right? So the reason Git does hashing is not for security. It's just convenience. This is actually, when you get down into the background of a lot of things, it uses hashing just because hashing algorithms strive for a lack of collisions. So if you want to take data and make it reliably unique based on the data that comes in, then hashing algorithms are the way that we kind of solve that. And while I use the password example to give you an example of like a way that you are probably already using hashing, that's not really relevant to how Git does things. So in the case of our Git repo, what happens is the SHA-1 hashing algorithm based on your code and stuff is most likely going to be unique, probably forever. SHA-1, like there are collisions that happen where, and by collisions I mean two separate pieces of data that end up having the same hash. That does happen, but it's very rare and it's very hard to get right. But I seem to remember that happening with Git repositories a couple of years ago. There was a problem with the hashing algorithm. That was a pretty cool thing to happen. So I think the way that you mean it is not the way that it works, but everything, the whole thing is stored in the binary file. So I'm actually going to go back to the screen share for a second. And let's take a look. So it uses the hashes. So then we never actually have two files that have the same name, right? And in that way, it can store everything that happened in your history without a problem. But the way that it, take a look at what it saves, this data is then turned into a binary file. So it has this text is turned into a binary file, it's compressed. And that is what is actually inside your objects directory. So this is 48 AAD. That's going to be this file here. So if we took a look at this, it's a binary file and it's gibberish, but this is like, imagine it was zipped up, so somewhere in here is that, the timestamp, but if you can read that, more power to you. You don't need Git. You're in the matrix. Yeah, of course. Now I think about it, I actually have no idea what Git uses to zip up those files. Probably gzip. That sounds likely.
I wonder if you could run like file on the files and maybe it would tell you.
Run what? Oh, there's a command called.
Yeah, I think you can
things every day.
and it might tell you what it is.
What is the command?
F-I-L-E. And then
okay, just
drop the path.
zlib. So yeah. Good call. And today I learned about the file command.
Yeah, that one's useful.
Actually, do you know if it'll tell you the right file type
In some instances, if it doesn't know what type of file it is, if it can't identify the file, it'll just call it data.
Okay.
That doesn't happen super often, but it does happen. But yeah, for the most part, it'll get it right. All right, well, it looks like we don't have any more questions. So thank you for the talk, Camilo. I learned a lot. I might need to watch it again because I'm a little like, what the hell? But that was really interesting. And I appreciate everybody coming. We'll see you next month.
All right. Thank you for coming, everybody. Bye.
Bye.